Hello everyone. I would like to present my steady and tilted hip prediction of square footing on expansive soil using a 3D numerical modeling approach. First of all, it is important to specify that the expansive soil is a worldwide problem and the damage caused by to buildings by soil expansive is very costly. In this context, we look at the problem of estimating the final heap of shallow foundations produced by soil winning and the factors involved. How and what approach? In addition, this research aims to discussion of expensive clay properties located in the Sufyan region, Batna province, Algeria. Develop a 3D numerical model of soil swelling based on a sample approach to numerical simulation of swelling pressure. And the final objective is the numerical analysis of the heap of square footing. The results are compared with the analytical methods proposed in the literature. This table presents the properties of soil located at Sufyan site. The experimental results indicated that Sufyan soil is a very plastic clay soil according to the LPCA classification compatible with the USCS classification. Moreover, the classification results from sample tests show that the Sufyan soil is characterized by a very high swelling potential. I move on the numerical modeling approach. A rigid concrete footing with a surface area of 1 meter 1 meter was considered. This footing is subjected to distributed vertical load increasing from 0 to 500 kilopascals and rests on layer homogeneous swelling layer 11 meter deep. The behavior of this clay is governed by an elastoplastic law represented by the Moore-Coulomb model. Because of the symmetrical nature of the problem, and to reduce the calculation time, only a quarter of the model is modeled. So the model was discretized by using primitive brick elements. In the initial state, the soil mass was subjected to gravity loading. Then a vertical pressure equal to 218 kilopascal constant over the entire depth was applied to simulate the swelling pressure of clay layer. The results indicated that there was a nonlinear decrease in heave with increasing footing load. The total heave predicted in the numerical study shows an excellent agreement with the analytical results of the Department of Army and Nilsson and Miller. An important application of this finding is that the footing continues to heave when the load is greater than the swelling pressure of 218 kilopascals. The heave was maximum at the heave was maximum at the soil mass surface, then it decreases with the depth. It can be seen that a differential heave of the foundation is observed at the end of loading. This figure shows the distribution of volumetric strength increments in the soil mass with load variation applied in the square footing. In all loading cases, zones of compression are formed at the base of the footing. These compression zones increase along with depth with load increasing, while maximum compression values are shown in contact zone soil footing. The effects of square footing amendment on the total heave was studied. The deviation have been selected from 0 to n.5 for distributed vertical loading equal 100 kilopascals. The results observed show that the increasing of the footing decreases linearly with an increase in the amendment region. In conclusion, it is important to note that the proposed numerical model based on the soil stress state expressed by total stress and swelling pressure can predict the heave of the soil mass loaded by a square shallow foundation. In the case of equality between the applied load and the swelling pressure, this does not mean a lack of heaving of the footing. The amendment of the footing influences the final heave. A linear decrease in heave observed with the increase in the deviation. Thank you for your attention.